Hello BC Calculus students, this is Mr. Johnson and this is section 4.8, which is on antiderivatives. You can look through the definition that's listed in the front of your notes there for the antiderivative as well as the theorem. We're going to try a few examples together, but all of this you have seen in previous calculus classes from last year. So we're going to find a function g such that the derivative of g is given by this equation. One of the things that we want to do first is we want to set up the function g prime in such a way that the antiderivative is easier. And that would be splitting apart this second fraction. So we would get 2x to the fourth, and then x, the square root of x would be x to the 1/2 divided by x. That would give us x to the negative 1/2. So in other words, we're just setting it up so that the power rule is possible. Our antiderivative then of g prime would be -4 cosine x plus, and then remember the power rule, you add 1 to the exponent and then you divide by that power, so you have 2/5 x to the 5th power, and we'll do the same thing here. We'll add 1 to get 1/2 and divide by 1/2, so we get 2x to the positive 1/2, and then this is a general antiderivative, so it would be plus c. And you could write this if you wanted to, or if you were trying to match this to some multiple choice question, for example, or multiple choice answer. You could write it as 2 times the square root of x. The rest of it, I think, would be just the way it's written there, and that would be the general antiderivative g. All right, let's try example number 2. So we're trying to find a specific antiderivative now because we have a condition. We have f of 0 is equal to -2. I'm going to rewrite the derivative of f as e to the x plus 20 divided by 1 plus x squared. And you might recognize that as the derivative of inverse tangent. So when we're trying to calculate the function f of x and we take the antiderivative of x prime, f prime of x, we get the antiderivative of e to the x, which is of course e to the x, and then we have the antiderivative of 20 divided by 1 plus x squared, which is 20 times the inverse tangent of x plus c. Now we're going to use our condition, which is that the function f is equal to -2 when x is equal to 0. So we're going to substitute in 0 here. And e to the 0 is 1, and tangent of 0 is 0, and so we end up getting c equal to -3. So your final equation for f of x would be e to the x plus 20 times inverse tangent of x minus 3. Okay, let's go ahead and try example 3. So in example 3, we're going to find the function f given the second derivative this time, which means that we have a condition for the first derivative as well as a condition for the function. So our first step is to calculate the derivative by taking the antiderivative of the second derivative of f, which is going to be 4x to the third plus 3x squared minus 4x, and we'll add c. And then we're going to use our condition, which is that the derivative of 0 is equal to 4. So we have 4 equals 4 times 0 cubed plus 3 times 0 squared minus 4 times 0 plus c. So c is 4, which gives us a derivative of 4x cubed plus 3x squared minus 4x plus 4. Okay, and then we're going to do the same thing, except this time we're going to calculate the function by taking the antiderivative of f prime, and we get x to the 4th plus x cubed minus 2x squared plus 4x plus c, and we'll use our condition that f of 1 is equal to 1. So we have 1 equals 1 to the 4th plus 1 to the 3rd minus 2 times 1 squared plus 4 times 1 plus c. And this gives us over on the right side the 1 plus 1 minus 2 cancels, so we get 4 plus c. And we can solve for c to get -3. So our equation for f of x is x to the 4th plus x cubed minus 2x squared plus 4x minus 3. Okay, let's move on to the next page. All right, so in example 4, we're going to look for f given f double prime. So similar to what we just did in the last problem, we have our two conditions. We're going to start with the derivative, which is equal to the antiderivative of f double prime. And x to the negative second would be the power rule. So we add 1 and then divide. We get negative x to the negative first power plus c. And we're going to use the condition that f prime of 1 is equal to 0. So that's going to give us 0 equals negative 1 to the negative first plus c, which means that c is equal to positive 1. So our f prime of x equation is equal to negative x to the negative first. Actually, you know what? I'm going to write that as negative 1 over x, and then plus 1 because c was 1 there. Okay, then we're going to do the antiderivative to get the function. So the function is equal to the antiderivative of f prime of x dx. And the reason that I wrote it as negative 1 over x is because the antiderivative is negative natural log of absolute value of x plus c. And we have our condition that f of 2 is equal to 0. So that means that we have 0 is equal to negative ln of 2 plus 2 plus c, which means that c is equal to ln of 2 minus 2, which is a little bit strange. So our function, our final answer, is that we have negative natural log of absolute value of x plus the natural log of 2 minus 2. Okay, we're going to talk about a topic that we've discussed a number of times throughout our chapters so far, and that's motion in space, motion along a line, motion along a parametric curve, and the idea of the position, the velocity, and the acceleration. And so this is just a review of that. If we were to take the derivative of position, we get the velocity, and if we were to take the second derivative of position, we get the derivative of velocity, which is the acceleration. So if we were going to go from acceleration and go backwards to find position, the integral of acceleration is going to be your general velocity, which is plus c. And then if you were to take the antiderivative of that, you would get your position. However, you would have the antiderivative of c, so you'll have something like a constant c1t, and then a second constant would form from that. And again, we'll have to have some conditions in there to actually find that. But with acceleration, if you took your antiderivative twice, you get back to the position. Let me show you an example of that. So in example 5, we have an object that moves along a straight line so that at any time t, its acceleration is given by acceleration equal to 6t. So at time 0, the velocity is 10. So v of 0 is 10. And the object's position is 7. So let's just call the position s of 0 is 7. And again, we have the acceleration as 6t. So we're trying to figure out the object's position at time 2. So we need a model for the position itself. So our first step is that we're going to integrate the acceleration, which is 6t, and that gives us 3t squared plus c. And that's going to be a model for our velocity, which means that we can use our velocity's condition at 0 to figure out what c is. So c is equal to 10. So our velocity is equal to 3t squared plus 10. So that's our first step. Then our next step is that we're going to do the same type of thing, but for the position itself. So we're going to integrate the velocity and that gives us t cubed plus 10t plus c. And again, we know that our position is 7 at time 0. So if we set this equal to 7 and substitute in 0, we have c equal to 7. All right, next step, we have our position equation. And what we need to do is figure out what our position is at time 2. So that gives us 8 plus 20 plus 7, so we end up getting 35, which is option D. All right, one more example on the next page. Okay, in this example, example 6, we're looking at a similar problem. We have the velocity, and it is of a particle moving along the x-axis, and it's given by that equation. If the particle is at position 4 at time 0, what is the position of the particle at time 2? So let's start by integrating velocity. This is technically a u substitution, but again, I'm hopeful that if you do the antiderivative enough, especially in this class, that we're able to come up with the antiderivative by just sort of thinking through what the multiplier would be. So in other words, if you were to take the derivative of cosine, you get sine, negative sine. So we know it has to be negative cosine as an antiderivative. And then the 2 right here, that multiplier, if we were to derive it, would be the chain rule times 2, but we're doing the antiderivative here, so it's going to be the 1/2. In other words, if we take the derivative of this, we get sine of 2t. And then we have a plus c, and this is going to be our, we'll call the position x of t, because it seems like they're sort of doing that in the problem. So that's our position x of t. We know that x of 0 is 4, and so we're going to use that to figure out what c is. So we have 4 equal to 1/2 cosine of 0 plus c, and cosine of 0 is 1, so we have 4 plus 1/2, which is 9/2, and that's our c value. So our position is equal to negative 1/2 cosine of 2t plus 9/2. And we're going to evaluate this now at pi over 2. So we get negative 1/2 times cosine of pi plus 9/2, and cosine of pi is negative 1, so we get positive 1/2 plus 9/2, which is 10 over 2, which is option D, which is 5. Okay, that does it for section 4.8. Thank you.